Okay, significant figures, calculations, and dimensional analysis is today's class. Our first note is on significant figures. Numbers that represent measured quantities, and that's the key here. Measured quantities are limited in their accuracy. So scientists must know how to discern when to cut off a number to the appropriate level of accuracy. There are three rules that we follow. The first is that zeros between figures are significant. So if you have a number like 0.7007, these two zeros count when you count the number of significant figures. And there are four significant figures in this number. Two, the zeros that are at the beginning of a number are never significant. So the zero before the decimal place and the zeros before the number don't count. You only actually count the last two numbers here. So you could rewrite this number as 3.7 times 10 to the 1, 2, 3, 4. 3.7 times 10 to the minus 4. That would be two significant figures. So those zeros are only spacers in this case. The third rule is that zeros at the end count if there's a decimal. If somebody takes the trouble to write 7.0000, it means they've measured it to that level of accuracy. So that would be five significant figures. You count the number before the decimal place and the four zeros that follow. So 7.0 and 7.0000 are the same number, but the second number, the one with the extra zeros, has been measured to a higher level of accuracy. And of course, the level of accuracy that you can attain in the measurement is a function of how accurate the instrumentation you use. So if I use a ruler to measure something, I might be able to say this table is 1.8 centimeters thick. If I use calipers from a tool and die shop, then I'll be able to say it's 1.813. Maybe I'll get down to 3 decimal places of accuracy. So depending on the tool I use, I can get different levels of accuracy. Now sometimes people get confused in the use of significant figures because conversion factors, if they're exact, you don't count them into the significant figures reckoning. So for example, 1 inch is exactly 2.54 centimeters. 1 dozen eggs is exactly 12 eggs. So you don't say there's two significant figures in a dozen eggs because 1 dozen is exactly 12. You don't even mention it for significant figures in that regard. In calculations, when you have multiplication and division, the product, the answer of the multiplication of the division, contains the same number of significant figures as the least accurate number. So for example, if you were multiplying 12.0 times 12, you'll notice that this number only has two significant figures. Your answer is going to be 144. But if you want to follow the rules of significant figures, you can only report the answer to 2 places. So you have to write your answer as 1.4 times 10 to the 2, which rubs most scientists the wrong way. That's why I put that little comment here. Because you know the answer is 144. 12 times 12 is 144. But according to the rules of significant figures, because there's only 2 significant figures here, you can only write the answer down to 2 significant figures. And that's important when you're compiling a whole series of data, and then one of your results is less accurate than the others. That one inaccurate result compromises the accuracy of the rest of the experiment. You can't have an experiment that goes to 3 decimals of accuracy if one of your measurements only goes to 1 decimal. It would make no sense. It's like trying to say, I don't know, weigh an elephant on a truck scale, and then a fly lands on the elephant, and you write down the difference in weight. It wouldn't make any sense because the truck scale only notices about 5 pounds in 5-pound increments. The second rule in calculations is that additions and subtractions, when you round your answer, you have to round it to the same amount of decimal places as the least accurate number being added. So for example, if you're adding 3.1 plus 2, your answer is 5.1, but you can't report 5.1 because 2 has only 1 significant figure, and you're only allowed 1 significant figure in the answer. So the answer has to be rounded down to 5. That's a 1 significant figure answer. Moving on to the next board, the third rule says that round numbers according to the number after. Okay, so if you have 5 as the second number after the one that you're going to round, you round up. So here's an example. You have the number 3.24 and you want to round down to 1 decimal place, the answer is going to be 3.2. If on the other hand you have 3.25, you would round up and the answer would become 3.3. And the last rule, and one that is perhaps the easiest to forget, is to keep excess decimals until the end of a calculation. then round at the very end when you report your answer. Do not round during a calculation, because if you do a multi-step calculation, you're going to introduce rounding error. If you round each time you get an answer, at the end you're going to get the wrong answer. So always, whenever you start a new calculation, you restart the calculation with your unrounded number. Okay, now we have some examples where we're going to use the rules of significant figures. From your textbook on page 24, one of the practice exercises asks, if a sprinter covers 100 meters in 10.5 seconds, what is his average speed? So we're going to use the rate equation. Rate times time equals distance. Now mind you, when you use this rate equation, it doesn't have to talk about cars driving or people running. It could be something like somebody eating ice cream cones. You could eat 3 ice cream cones a day. If you eat for 3 days, how many ice cream cones do you eat in those 3 days? The answer would be 9, because days cancel. But here we're asked for the rate, the average speed of the runner. So we're going to transpose the time. We know the distance is 100 meters, and we know the time is 10.5. So we're going to transpose the t, and we're going to solve for r. 100 divided 10.5, you'll see that meters cancel, and your answer is going to be in seconds. You'll notice that the denominator of a denominator becomes a numerator. So the answer is in seconds. Oh, I put the rate. This is the time should be, that's the rate. Time is 10.5 seconds. Okay, so I wrote that. Just a little mistake. And we get a rate at the end. Okay, so the rate, I transposed the t, not the r, because I wanted the rate. The time is given and the distance is given. So 100 meters divided 10.5 seconds gives you a rate of meters per second. This is the answer you're going to get in your calculator readout. But we can't report that level of accuracy. Your most accurate number in here only has three figures in it. So your answer can only be reported to 3 figures. So we're going to write 9.52. You notice that 3 rounds down to 2. So the answer is 9.52 meters per second. Question on page 25 shows a big long problem. You're going to see it. The answer is 2 decimal places. So we'll just skip that for that. You'll see it when you get your handout. In dimensional analysis, you need to convert from one measurement to another by using a conversion factor. And the key to using conversion factors properly is to write them as a fraction. When you write a conversion factor as a fraction, there's 2 ways you can write it. For example, how many eggs are in a dozen? A dozen can be expressed as 12 eggs per 1 dozen, or 1 dozen per 12 eggs. It means the same thing, but you have to use the right one when you're converting it, or when you're doing it, or when you're using that conversion factor in a calculation. So if you have 3 dozen eggs, how many eggs do you have? Now everybody can say 36, but if you want to show it with proper mathematical technique, you have to say 3 dozen times 12 eggs per dozen. How did I know to use this conversion factor? Because I wanted to cancel out dozen. So I put dozen in the denominator here, because it's in the numerator here. Dozens cancel. 3 times 12 gives you 36 eggs. I ask you here to convert 1 mile into millimeters. And the following conversion factors are needed. There are 4 conversion factors to go from a mile to millimeters. First, it's that a mile has 5,280 feet. And that gives rise to 2 conversion factors, either 1 mile per 5,280 feet or 5,280 feet per mile. And at some point you're going to see that we're going to use one of those 2. 1 inch is 2.54 centimeters, 1 foot is 12 inches, and 1 centimeter equals 10 millimeters, each with the conversion factors that result. They always give rise to 2 different conversion factors, but that mean the same thing. We're starting off with 1 mile, and we want to get rid of the mile, so we're going to put the conversion factor that has feet going to miles with the mile on the bottom, because that way the denominator cancels with numerator. The conversion factor is 5,280 feet. Then we have feet left over, so how are we going to cancel feet? We're going to put the conversion factor with inches to feet, with feet on the bottom, feet cancel, and you get times 12. And so on down the line. When you multiply all these conversion factors, and remember, when something is in the numerator, you multiply it, and when it's in the denominator, you divide it. But we have all 1s in these denominators, so we don't have to worry about the denominators. We're just going to multiply all these numbers through. 1 mile is exactly 1,609,344 millimeters. this is an exact number. There are no significant figures to worry about here. Why? Because all of these conversion factors are exact. 1 foot is exactly 12 inches. 1 centimeter is exactly 10 millimeters, and so on. The choice of conversion factors is made by determining which of the two fractions, each one of these conversion factors gives rise to two fractions, which one of the two fractions are paired so that the appropriate unit is cancelled. On page 27 of your text, on the practice exercise, it asks you to convert 28 miles per gallon, which is a level of fuel efficiency that a certain vehicle has, into kilometers per liter. So you need to know the conversion factor from miles to kilometers, and I use the one that's the back cover of the book. This is not an exact number. You see, this would be the exact number, 1.609344, but I just used to 4 decimal places, because you'll see here that there's only two numbers in this original number. So that's not going to require us to have more than 2 decimal places, 2 numbers in our final answer. So I'm not too concerned if I used 1.6093, although I'm breaking the rule of not rounding during the calculation. But suppose that this is what you were given. So 28 miles per gallon times 1.6093 kilometers per mile times 1 gallon for every 3.78 liters will give you this number. So what I'm doing in my calculator is 28 times 1.6 divided 3.78. I'll get 11.903734. I'm only allowed 2 significant figures, so I have to round this to the closest one. 11.9 rounds up to 12. So the final answer is 12 kilometers per liter. The second question on page 28 of your text asks you to convert 5 cubic feet to cubic meters. And we did a little bit of this yesterday, but we're going to go from feet to inches, from inches to centimeters, and from centimeters to meters. And we should, by this point, start recognizing the conversion factor. There's 12 inches to the foot, 2.54 centimeters to the inch, and 1 meter per 100 centimeters. And how did I choose them? I used that criterion of canceling the thing before it. So feet cubed has to cancel with feet cubed. But I only have feet to the 1 here. How am I going to get it to be cubed? I'm going to cube the whole conversion factor. Of course, that means I have to cube the 12, the 1, the inches, and the 1. And I rewrote it down here to show you what it looks like when I've expanded it by putting the powers in. So 12 cubed is 1,728. Inches cubed is written here. 1 cubed is still 1, so I didn't bother writing the 1. And feet is cubed as well. We do that all the way through, and then we say 5 times 1,728 times 16 divided 1 million. You'll notice that 100 cubed is 100 times 100 times 100. That gives you 1 million. Final answer is 1.4 times 10 to the minus 1. And when I write my final answer, I have to look which one of these numbers, if any, has a limiting number of significant figures. And that would be the first number, 5.0 cubic feet. All these are conversion factors, so they're exact numbers. You don't have to worry about them. But this is a measurement, and it's only got 2 significant figures. So the answer can only have 2 significant figures, and so we round this off to 0.14 meters cubed. Okay, now, that's a lot of material. Did you pick up anything in there that you would like clarified or repeated? Would you like to see the first board? Maybe? Still recording.
Does 3.25 necessarily have to be rounded up?
Does 3.2 necessarily have to be rounded up? I've read about cases where sometimes if the number if the number before is even, they round down. If the number before is odd, they round up. They do all sorts of funny stuff like that. But really, statistically, if you just round up when it's a 5, it averages out anyway. And it doesn't give you any real advantage to follow complicated rules. So whenever the number after the number that you're rounding is 5, just go up. Okay, anything from the conversion factors? Okay, yeah. No? Okay. Well, in that case, I have one last question I'd like to do. I'd like to try this question from the book. It says benzene has a density of 0.879 grams per milliliter. Calculate the mass in grams of 1.0 quart of benzene And here are the conversion factors. 1 liter equals 1.05 quarts. 1 centimeter cubed equals 1 ml equals 1 cc. You'll sometimes see that written on the side of a syringe. These three are interchangeable. And then use the density formula. Density equals mass over volume. Final answer is 832 grams, but what I want you to show me is the intervening work. All the work in between that gets you this answer. So you can stop it there.